Next up, we've got Ron Green, the Institute scientist with the Southwest Research Institute, talking about using remote sense data to improve recharge estimates. Thank you so much, Ron.
Good afternoon. So I appreciate the opportunity to share some discussion of a recent project that we've undertaken at Southwest Research Institute. I think Wade's helping me out here, buddy. Good. Thanks, Wade. So this is some work that we've undertaken at Southwest Research just over the past several months, and I would like to recognize Stu Stadoff, my colleague. He's the one doing a lot of the heavy lifting. So this talk's going to be divided into two parts. The first part talks about recharge and soil moisture, sort of in the perspective of from a hydrologist and why that's important to all of us here. And then the second part addresses the use of some recent platforms, some recent satellites that are providing some rather useful data that we may be able to use to get a better sense of soil moisture and recharge. So I think we all understand the importance of recharge, but maybe we don't fully appreciate how important it is to some of the problems that we face. So, the amount of discharge, the amount of water coming out of a system is wholly a function of how much water is going in, the amount of recharge. We oftentimes use the DFCs in order to determine the MAG, calculated with the GAM. And in reality, the amount of water that you have is a function of recharge. It may not be all the recharge because you have to account for stream flow, spring discharge, and the like. Oftentimes, recharge is the source of the greatest uncertainty in the water budget. So it's really important to understand recharge as best you can. A lot of the models, as Wade was just talking about, are highly dependent upon recharge. Some of these models out in West Texas, for example, you may go from a 1/4 inch to a 1/2 inch of recharge. You can say, well, that's not that much, but that's doubling the amount of recharge. And a lot of times that's all you have to work with. Recharge is highly variable. It's not a constant. You can't figure it out one year and that's good for the next or whatever. You have, around in this area, you have, 2 years of flooding followed by 2 years of drought. So it's getting recharge is a real challenge. If you have an enclosed watershed, the amount of the recharge is all coming from precipitation. So you start with precipitation and then you try to understand how much recharge is coming out of that. And so we're looking at different ways to understand recharge. Many people are trying different things. They're all very good. What I'm talking about today is the use of satellite data. So it doesn't mean those other approaches aren't good and will not lead to very good results. I think it's important to pursue all these. So I'm going to just put this in context of a site, a particular site, the Devil's River. We've been working out there for a period of time. And here are 3 images of precipitation out in the Devil's Watershed, 3 different dates. Large events, several inches of rain, and you can see they're very different. So just depending upon the model that you use, you're going to make different predictions. And certainly where that rain goes and how long it takes to go through the system is going to affect the discharge differently. So, recharge, when you start with precipitation and you're going to recharge, there's a lot of different factors that come to play. The frequency, duration, but what's one thing that's very important is the antecedent moisture content, and that's how long the water stays in the ground after a particular rain. So You know, if you have one rain and it's, you know, you wait a couple weeks and then you have another rain, you're going to have a pretty good recharge. But if you have one rain and it hasn't rained in several months or longer, you're not going to have very much recharge. That's the antecedent moisture. And it's highly effective in determining how much recharge you get out of precipitation. And in addition to that, you have all the different things with humidity, soil type, vegetation, and the like. So out in the arid and semi-arid parts of Texas and elsewhere, what you see is that, you know, what people think is that recharge goes to zero as precipitation goes to zero, and that's that orange line on the left. But that's not what happens. You have a certain threshold, and what you see is that recharge goes down to zero, down to some threshold, and out in that area it's 15, 18 inches, and then below that, you do not get distributed recharge. Below that, you get something called focused recharge, and that's where, you know, surface runoff will go down into, you know, riverbeds and the like. You still get recharge, but you don't get that much. But even though it's not that much, it's extremely important out there because that's what recharges the aquifers. That's all the water that they have to deal with. So, you know, on the one side, you have the distributed recharge, and that's where precipitation falls on the landscape, gets underground. Lower than that threshold, you have this focused recharge where, yeah, it's much less, but it's very important. And it's important to understand both these. So sometimes out in these areas, you'll get distributed recharge. Other times you may get focused recharge. And so the duration, the frequency, and the intensity of precipitation determines what kind of precipitation and at what rate you're getting. So out in the hill country, we've used a certain method to get recharge. There are other methods out there. We use stream discharge. And if you calculate the baseflow portion of the stream discharge, you interpret that to be the amount of precipitation you've gotten distributed. So that goes under the ground when it's distributed as precipitation, flows underground to the streams, discharges into the streams as springs, and that's your amount of recharge. So if you can measure how much water's in that spring, that's due to just the base flow, not the surface runoff, and then you see the area that's being contributing to that area, that tells you how much recharge you have. So just looking out in the Devil's River area, you know, Del Rio's down here, this is Big Bend. You see that you're out in this area that transitions from humid, subtropical, semi-arid. Semi-arid is usually around 20 inches of rain on average annually, then over to arid. So you're going from distributed recharge to focused recharge in this area. So it's a real challenge to understand how much recharge there is. So we took those numbers from the spring discharge and converted those through some manipulations into the average recharge over this area, and we correlated that with precipitation. And we came up with this relationship. So this is how we got that threshold of 15 to 18 inches. So the blue dots and the blue line are data from the hill country. And, you know, looking about the technical literature, we see that, oops, sorry about that. You know, we see that, you know, there's other places. This happens to be South Africa. There's other places in India that have the same environmental conditions that have very similar relationships. So you have some threshold. Now, if you have a desert up in Mongolia, for example, it's going to be quite a bit different. But for these similar settings, you get the same relationship. So once again, you have distributed recharge and focused recharge. So yeah, I mentioned the importance of antecedent moisture content. So when we were doing models out in this area for different parts, we would take the precipitation and try to convert that into recharge, but we had to take into account the antecedent moisture content. That was an important factor. And the only way we could deal with it was as a calibration factor, so we would adjust it. You know, we started out putting 6 months of the previous precipitation in there, and that would determine antecedent moisture. Well, out in that area, it turned out to be 1 or 2 months, but that was just by calibration. So, you know, it's very hard to measure these things directly. So that's where we've come from, and now we're going into this phase where we're going to try to use remote sense data, and by that I mean from satellites, from different platforms up there, and just see how useful this might be. Well, if you just take a step back and see what's going on in the satellite world, you see that over time, there's been a number of satellites, but there's been a little explosion in the amount of launches that are sending up scientific satellites. I mean, it's just taken off. So there, in the past there were, many different missions. There were satellites put up there for communication, GPS and the like, but there are many, many, many satellites going up these days for scientific purposes. And so that's what we're trying to take a look at to see how useful they might be for us to calculate or estimate or resolve recharge and soil moisture. So the other thing is to look at what's the size of these satellites. Well, back in the day, and even currently, you have these satellites that weigh tons. They weigh 15, 17,000 pounds for communication purposes. What we're talking about here are these much smaller satellites that we can use for scientific purposes. And they call these things CubeSats. And they're the size of something smaller than a volleyball. They weigh just 3 or 4 pounds maybe. And they're very small, and they can send up many of these in a single launch. They can send up 30 of these in a single launch. And when they send them up and they're all part of the same system, they call them a constellation. So the problem is there's no single satellite up there that can measure recharge or soil moisture. So soil moisture maybe a little bit more, but not recharge. So what we're going to do is to try to see if we can integrate the signals or the information from a number of satellites, platforms, to come up with this information. So we're going to try to pull all this together. So we're looking at which satellites up there are of interest to us. Now, if you're trying to figure out some information for a humid area, it's going to be different than what you're going to be using arid and semi-arid. Over in the humid area around Houston, for example, you may be much more interested in flooding issues. So that may be a motivation to use different satellites from what we are interested in using out in the arid and semi-arid areas. So if we look at the area where you're transitioning between distributed recharge and focused recharge, you're looking at about half of the state of Texas. You step back a little bit and you're looking at about half of the United States. So if this works, it could be applicable not only to a good chunk of Texas, but elsewhere. So, once again, stepping back and looking at all these satellites up there, there's an awful lot of them up there. And so Stuart has sat down and gone through these to see which ones are more useful. And what he's decided is that the spectrum of interest for this is the visual, infrared, and the radar spectra. So it's right in this area. So he's looking at those platforms up there that can give information in this area. And so going from the sort of older ones to the newer ones, and they're all new, relatively speaking, there's Sentinel that was put up in 2014, and it's an active system, meaning it sends a signal down, and then it gets the radar signal back. And this has been there are two of these, and it's a 2-satellite constellation, but between the two of them, every 6 days, it crosses over and gives this information. And this one, as we'll see, is very good at constraining where rainfall actually lands on the ground. Another one was SMAP. This had great hope and expectation. The A and P stood for active and passive, but the active part died out after just a few months in space, but it's still quite useful, where they just get the emissions coming up. It's over a large area, and so they're getting large-scale radar images with SMAP. So it's still quite useful. This is 2015. Going up to 2016, this happens to be a constellation mission that was developed by Southwest Research and others, and it is 8 satellites, And these are those CubeSats. They're small. So there's so many of them that they get 3 or 4 passes a day over the Earth. So they get very high resolution time-wise measurements of whatever it is it's measuring. And what it uses here is it looks at the GPS signal that's being bounced back, that's being emitted up. So it's not sending out a signal, it's using the GPS. So, there's a lot of innovation that's going on. The GOES system, this particular one just went up recently, but this is the 16th of a series of these. They're much higher. They're geostationary, so they stay over the same part of the Earth. And so the one that has been recently deployed is over the East Coast. In the next few months, I believe, the West Coast will be. And this gives us visual infrared, so that gives us temperature and soil moisture in the atmosphere. Pardon me, moisture in the atmosphere. And then there was one that perhaps you've heard of. It's called GRACE. It was a gravity system, and it could detect the change of water due to the change in gravity over time. But it was decommissioned a couple years ago. It operated very well for about 15 years, and there's going to be some other missions to replace this. But it's been a very good. Satellite gave very good data. But when it looked at the column of water, it would measure the entire water, where you could remove the surface water, so you're left with soil moisture and water and storage. So you could calculate the change in water and storage in large aquifers like the Ogallala and others, but you had to know soil moisture. They did not know soil moisture well enough, so they had to estimate that, so that increased the uncertainty in that measurement. If you have a way to get soil moisture, then data like this is going to be much more valuable. So these are the 4 systems that that Stu has settled on to put together. And you can see that they only go 2 to 5 centimeters. They're just looking at the soil moisture at the top part. But if that can give us insight on a couple things, namely antecedent moisture, and if there's surface water, it's going to be very valuable, because we can go back to those models where we have to assume things and we have insufficient data, high levels of uncertainty, and improve that. Those models are going to be that much better. So, you can see there's SMAP, Sentinel-I, CYGNSS, and GOES. So the idea is to bring all these together to try to figure out better what's going on with soil moisture and recharge. So, radar, if you notice, 3 of those give you radar data. So there's a lot that can be understood from radar. If you can start to determine, what some of these factors are that change the radar signal, plowing, irrigation, and then remove those and get at the soil moisture, then you can understand much better what's going on with the soil moisture issue, which leads to better thoughts of and estimates of recharge. So, the way that these satellites read these data, interpret these data, vary from satellite to satellite. And that's why you want to use these different platforms. So one issue is the scale. One of the limitations of the GRACE was it was 1 degree, so it only looked at large aquifers. It was about 60 miles across. You see these other missions are getting smaller. 40 kilometers for SMAP. CYGNSS is 25. GOES is 14 kilometers, and that Sentinel is just almost a point measurement. So you start putting these together, you overlap them, you get information, and you can use some rather sophisticated algorithms and methods in order to really tease out some good information. So this is just shows a little bit more on the CYGNSS data. So the CYGNSS system, if you recall back from the title, it's to look at cyclones. So it was put up there to look at cyclones, and so because of that, it just stays between plus and minus 38 degrees latitude. Because these tropical storms aren't north of that or south of that. So what they're trying to do, what Stu's trying to do, is take this information and understand better, between the soil moisture and the surface runoff. So if you can determine where surface runoff is, and you're looking at it 3-4 times a day, you can find out those areas in the arid landscape, for example, where you're having surface runoff, and that's telling you have focused recharge. One other issue that we bumped up against, this was when we were modeling the Devil's River. We use NEXRAD data, which is very good data, but what we had was a discharge event down in Pafford Crossing, where Devil's River discharges into Amistad Reservoir, and there was a significant discharge event, but there was no rain event associated with it, with NEXRAD data, which tells us that the NEXRAD data did not pick up this storm. So either that storm was outside the capture area or something else was going on. So if we can use a Sentinel in order to improve our understanding of when and where and at what rate precipitation is falling, then we can avoid these situations. So that kind of sums up where we are with this project. We do have some areas that we're using these data. I think it's a very fruitful area for further development, and that's the Imperial we, Stuart's going to be working on this diligently. He promised me over the next 9 months to put these things together, come up the idea is come up with these algorithms, come up with these automated systems so that you can account for plowed landscapes. You could come up with irrigation, so those things don't necessarily bias your unduly the information that you're trying to tease out of these data sets. You can use, then you don't have to use ground-based stations, eddy covariant towers or whatever for your measurement of soil moisture. You use those as ground truthing because they're few and far between. They're very good, but they're expensive and it's hard data to get. But if you could use those to ground truth this other information, that makes those data much more valuable. And then we're trying to integrate these data sets to the best possible. There's a lot of opportunity here, and we're going to pursue that to see just how far we can to get this better understanding of recharge and soil moisture to support these models. So I believe that's it, and I'd be glad to answer any questions. Thank you.